Pop quiz, 5 seconds. Which reagent turns a primary alcohol, like 1-butanol, into an aldehyde without over-oxidizing it? A. PCC. Letter B. Hot permanganate. C. Ozone. Or D. Sodium borohydride. Time's up. The answer is A. PCC, pyridinium chlorochromate. It stops cleanly at the aldehyde. So from 1-butanol, you get butanol, also called butyraldehyde. And that's just one strategy. In this video, you'll learn the key methods to make aldehydes and ketones, oxidizing alcohols, slicing alkenes with ozone, building aryl ketones by acylation, and selectively reducing carboxylic acid derivatives. Along the way, we'll point out common pitfalls and highlight the go-to reagents. First, the big idea. Aldehydes, written as RCHO, place the carbonyl group at the end of a chain, while ketones, written as RCOR', position the carbonyl in the middle. That polar carbon-oxygen double bond is a synthesis magnet, attracting a range of transformations. Because of that, chemists need reliable ways to create carbonyls. One straightforward route is to oxidize a primary alcohol with PCC or Des-Martin periodinane. In this reaction, RCH2OH becomes RCHO, an aldehyde. The key is to keep conditions anhydrous without water, so the aldehyde doesn't get over-oxidized to a carboxylic acid. If water or strong oxidants are introduced, the reaction quickly goes further than you want. That's why one pitfall to watch for is using reagents like Jones. Under aqueous conditions, it won't stop at the aldehyde. It drives the reaction all the way to the carboxylic acid, so it's better reserved for other purposes. When that direct oxidation approach isn't suitable, the focus shifts to selective reductions. One option is to start from a carboxylic acid, convert it into an acid chloride, and then carefully stop at the aldehyde, using lithium aluminum tritert butoxyhydride, or by performing a Rosenmund reduction. Another approach is to begin with esters or nitriles and reduce them to aldehydes using diisobutyl aluminum hydride, better known as DIBAL-H, at -78 degrees Celsius. In all these cases, control is crucial. Without it, the reaction overshoots the aldehyde. So far, we've seen two main routes: oxidizing primary alcohols to aldehydes and using selective reductions from acid derivatives and esters. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Now, let's turn to ketones. Secondary alcohols oxidize cleanly to ketones with reagents like PCC or Jones. In these reactions, the carbon framework stays intact. No carbon-to-carbon bonds are broken. Building on that, another powerful route is ozonolysis. Here, ozone cleaves a carbon-carbon double bond. With a reductive workup, each alkene carbon becomes a carbonyl. Internal or disubstituted alkenes give ketones, while terminal alkenes can produce formaldehyde at the chain end. If your goal is to place a ketone directly on an aromatic ring, a different strategy comes into play: Friedel-Crafts acylation. In this reaction, benzene reacts with an acyl chloride in the presence of aluminum chloride to form an aryl ketone. This method avoids carbo-cation rearrangements, and because the new carbonyl deactivates the ring, over-acylation is unlikely. For even greater control, especially when starting with an acyl chloride, a Gilman reagent can be used. This reagent adds just once, giving you a clean ketone. By contrast, Grignard reagents usually add twice, driving the reaction toward a tertiary alcohol, which is not the target here. Of course, every method comes with its cautions. For example, with DIBAL-H, temperature matters. Keep it cold to stop at aldehydes. With ozonolysis, the type of workup decides the outcome. A reductive workup preserves aldehydes or ketones, while an oxidative one pushes them further to carboxylic acids. PCC must be kept dry, and as always, niche tools exist for very specific positions or transformations. So, to bring it all together, here's a quick rewind. First, choose the pathway that fits your starting material. Next, pay attention to solvent, temperature, and workup. Finally, select reagents that stop at the carbonyl rather than pushing the reaction past it. That's the essence of smart carbonyl synthesis.
Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet, content made just for you.